All right, so what we're doing today is we are starting into chapter 6. And chapter 6 is all about intermolecular forces. And so we're going to start today with kind of a simple question. What holds a sample of a substance together? What kinds of factors might impact physical properties like vapor pressure or boiling point? So what I want you to do is I want you to think about this for about a minute and put your answers into the chat or bring them up somehow when we go into group discussion. Try to answer these two questions, and in about a minute's time we'll talk about some of our answers. So go ahead. All right, we've got some answers rolling in here, and they're kind of falling on the same theme. The answers that seem to be coming in the most popularly are inter and intramolecular forces. Silas said the attraction between the positive and negative parts of the molecules, at least in part. Jacob Rice saying things about electronegativity, gravity, and friction. Luke's talking about intermolecular forces. So yes, the answer here that we are looking for is something called intermolecular forces. Intermolecular forces are forces that exist between molecules of a substance. And in particular, again, we want to make a distinction here between an intermolecular force, that is a force that exists between molecules themselves, and intramolecular forces, forces that exist within a molecule, which we know better as bonds. So intramolecular forces, bonds, actually don't have a whole lot to do with physical properties or kind of holding a substance together. They hold an individual molecule together. But when it comes to how does one molecule interact with another, bonding really doesn't have a whole lot to do with that. We can make an argument that molecular shape does. We can make an argument that polarity does. But the actual bonding itself doesn't have any real role in determining whether something is going to dissolve in water or boil at a higher temperature or a lower temperature or anything like that. And so in total, these intermolecular forces that exist are dictated by the polarity of the molecules in the sample. So polarity does play a significant role. This is why we spent a good bit of time last week talking about polarity in molecules, being able to identify a polar molecule versus a nonpolar molecule. Because if the molecule is polar, then it's going to exhibit completely different types of forces than nonpolar molecules. And in some, these forces at play are your stronger intermolecular forces. The nonpolar forces, by contrast, your London dispersion forces, your induced dipoles, these are significantly forces than the polar forces. So we can break down intermolecular forces based on the polarity of the molecule. Polar forces are going to exhibit one or more of these. So at the very base, they can exhibit dipole-dipole forces. Certain types of polar molecules can exhibit a special, stronger form of dipole force called a hydrogen bond. And polar molecules in general can interact with ionic compounds to make ion dipole forces. And this is the kind of thing that happens especially in water. When we dissolve a molecule like sodium chloride or any other kind of ionic solid in water, is the ion dipole forces that ultimately hold together that solution and stabilize that solution. In the nonpolar side, we have the London dispersion forces. We'll get more into that later. We also have what are called induced dipoles, where a polar molecule impacts a nonpolar molecule and causes it to temporarily polarize, and that does create a slight attractive effect, but it's considerably weaker. So what I'm going to have you do is, there is some information here in slides 7 through 18, as well as your textbook. In your textbook, let me update this slide for you. We're talking pages 255 to 266. So let's cross this out. Pages 255 to 266 in your textbook have information on the details of intermolecular forces, as does slide 7 through 18 here. So what you're looking for, I sent in an announcement and an email this morning, a document. You should have it in your lecture packet as well. It looks like this. Oops, that one. It looks like this. I'm going to break you into groups of 4, and what I want you to do, get into your breakout rooms and talk through this, work through all of this. So this picture should look familiar. We just talked about it. But go through and try to do all of the critical thinking questions for each of the models. Do as much as you can. What I'm going to do is I will post the key to this in Blackboard, and then I will also publish a supplemental video on YouTube where I walk you through the answers to this, and show you how I would look at it as a way to check your answers. So what I'm going to be doing, I will release this to you. All right, so go ahead and go into the breakout rooms. I'll be hopping around and joining you as we go. All right, so let's walk through the intermolecular forces here, and let's go through the pages of this particular activity. So in Model 1, we are asked, what is an intermolecular force? And so this is what we started off the topic with, and I was looking at the difference between intramolecular and intermolecular forces. When when it comes to molecules, molecules are dominated by intramolecular forces, meaning we have bonds that hold together these atoms. And so I've got a covalent bond between this hydrogen and this oxygen. I've got a covalent bond between this hydrogen and this oxygen. Those are intramolecular forces. Intramolecular forces, again, we've got to think about here as bonding. Now, intermolecular forces, these are the forces that hold groups of molecules together. So there is some attractive force that exists between molecule 1 and molecule 2, and molecule 2 and molecule 3. Those are intermolecular forces. So to answer the questions here, we're asked what specific molecule is inside the box in figure 1. Well, we can see it's H2O. H2O, it's going to be water. In relation to the box for molecule 1, where do the intramolecular forces exist? Inside the boxes or outside the boxes? The intramolecular forces, the ones that are designated by stars here, these are inside the boxes. Again, intramolecular forces are bonds. These are inside the boxes. Based on the intramolecular forces for molecule 1, draw similar asterisks for molecules 2 and 3. That's easy enough to do. So we've got one there and one there. We've got one there and one there as well. So those all exist in those bonding spots. In relation to the molecule, where do the intramolecular forces tend to occur? Inside the molecule or outside the molecule? Again, we've kind of already answered this. They are inside the molecule because they are the chemical bonds that hold the molecule together. We are told that two intermolecular forces exist in figure 1. Are they positioned within the molecules or between the molecules? We can see that these dashed lines are definitely between the molecules. So we would say between. Right, scrolling down to some other ones. Question 6. What is the difference between intermolecular and intramolecular forces in terms of where they occur? So what we can say is intramolecular forces exist within a molecule and are better known as bonds. Intermolecular forces exist between molecules. Okay, so now we move on to model number 2. Model number 2, we're looking at the 3 different types of intermolecular forces. The dipole-dipole interactions, the hydrogen bonding, and the dispersion forces. And so we can see that in figure 2 here, we have dipoles. That is, we have molecules with positive and negative ends. We talked about dipoles in chapter 5. These are your polar molecules. And so we can see we've got positive ends here. We've got negative ends here. And so we can see that there are some forces that exist between the positives and negatives. There are forces that exist between the positives and positives, and there are forces that exist between the negatives and the negatives. So question 7, figure 2 represents an arrangement of 5 molecules. What is the difference between the two ends? One end has a negative charge, the other end has a positive charge. That's really the big difference between them. There's nothing too complicated there to discuss. Molecules with the property that we have identified here are known as dipoles. What is a dipole? A dipole is a molecule that has a distinct positive end and a distinct negative. That's the definition of both of those. If we consider the attractions here, so going to number 9, if we consider those attractive forces, where do they occur? Well, we can see that the only times we see attractive forces, these heavy dashed lines, are when a positive is interacting with a negative. And repulsive forces only occur between like charges. So when positive interacts with positive, or negative interacts with negative. So the forces described in 9 and 10 are dipole-dipole interactions. How might dipole-dipole interactions help many molecules attract each other? Well, if I've got a bunch of these aren't the only interactions that are going to exist. Obviously, I've got some interactions here that haven't been drawn in yet, but this negative and this positive are going to attract each other. This negative and this positive are going to attract each other. This negative and this positive are going to attract each other. So our answer here, a combination of all of the attractive forces between the positive and negative poles will help the molecules attract each other better overall. All right. Continuing on. A dipole is often found in polar molecules when the electrons are unevenly shared. This uneven sharing gives a partially positive charge given by the Greek letter delta, positive, and a partially negative charge given by the Greek letter delta, negative. A couple of questions came up in the session about this. The deltas here, the delta positive, the delta negative. The Greek letter delta here indicates a partial charge. So we're talking about something that's either less than +1 if it's delta positive, or less than -1 if it's delta negative. So what causes the dipole in polar molecules? It's the uneven sharing of electrons in a molecule. For number 13, what symbols are used to represent the partial charges? Delta plus is used for partial positive. Delta negative for partial negative charge. All right. In this diagram below, the hydrogen iodide molecule has been drawn with its partial positive and negative charges. Using the three molecules, draw an attractive force between two hydrogen iodine with a dashed line and repulsive forces using a dotted line. Okay, so very similar to what we saw in the previous example. We're going to draw dashed lines between the positives and negatives. And then we will draw dotted lines between any of the repulsive forces that exist. So the two hydrogens are going to repel each other. The two iodines are going to repel each other. Because the negatives are going to repel each other, the positives are going to repel each other. And so that's all that we would be looking for in that one. For question 15, nonpolar molecules do not form dipoles because the electrons are shared evenly. Would we expect nonpolar molecules to stick together more or less effectively? Well, since they don't have dipoles and we don't have these positive-negative interactions, nonpolar molecules should be less effective in staying together than polar molecules. And last bit here, they want us to explain ourselves. Well, dipole-dipole interactions are going to involve attractions between positive and negative ends on molecules. These attractions will be stronger than no interaction that is present in a non-polar molecule. All right, so we've gone through and talked about dipoles. We've gone through and talked about, so let's move into the next part of the module. When a hydrogen atom is covalently bonded to nitrogen, oxygen, or fluorine, a very strong dipole is formed. So keywords there: nitrogen, oxygen, or fluorine with hydrogen. Dipole-dipole interactions that result from these dipoles are known as hydrogen bonding. hydrogen bonding is an especially strong form of that interaction. Why those three? Nitrogen, oxygen, and fluorine are very electronegative and have a very compact negative charge because they are so small. And so that combination of the electronegativity and the size means that we've got an extreme level of polarity there. So the next step here is to draw. We want to draw an ammonia. Two more ammonias. So I need a nitrogen and some hydrogens. So I'm going to do the same thing. I'm going to have delta negative around the nitrogen, delta positive around the hydrogens, delta negative around the nitrogen, delta positive around the hydrogens. And in number 18, I'm going to draw the attractive forces as dotted lines. So the negative nitrogen is going to be attracted to the positive on the hydrogens and attracted there as well. And there's going to be some attraction here as well. Indicate and label one covalent bond. Oh, and label? Okay. So these are hydrogen bonds here. These are covalent bonds here. For number 20, is the hydrogen bond the same as a covalent bond? No. Hydrogen bonds are an intermolecular force, not an intramolecular. Because covalent bonds are formed within a molecule through sharing of electrons. Whereas hydrogen bonds formed as interactions between molecules. How are they similar to each other? Both are attractive forces, but Covalent bonds are within a molecule. Hydrogen bonds are between molecules. And that's the big difference between them. All right, so let's move on to figure 3. So we've talked about polar interactions, hydrogen bonding, dipole-dipole interactions, those partial charges on those dipoles. Let's talk about dispersion forces. Dispersion forces are nonpolar forces. And for this, we're going to use an analogy. We're going to use Bob's sheep here. And we're going to compare Bob's sheep in the pasture to the electrons surrounding an atom of krypton. And so in this analogy, we know that Bob's sheep like to wander around the pasture. They can be found anywhere at any time. How are they distributed in box A? We can see here that they're distributed very evenly. And in box C, not as evenly. There seem to be more on the left side of the pasture than the right side. Now looking at the sheep in box C, are the sheep identify a woolly and a non-woolly area. So the woolly area would be this area right here. And if I draw a line of demarcation here, the non-woolly area would be right here. Now we're going to compare this to a krypton atom. So bear with me just 1 second. I'm going to, I've de-zoomed a little bit to try to fit all of this in here at the same time in the same place. If I look at B and D, how many protons are in each box? Well, the answer there is still 18. How many electrons are in each box? I'm going to use a stamp here to highlight them, but I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 in box B. And I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 here in box D. So 18 in each one. So is each atom electrically neutral? Yes. They each contain 18 protons and 18 electrons, so they are neutral to each other. But what we want to do is we're going to have to look at this a little bit more closely. And so if I go up to box B, I can see box B, yes, they are evenly distributed around the nucleus. The answer here is still yes. There are even numbers of electrons around that nucleus. But in box D, we can see that we have the same kind of problem that Bob Sheep had in box C. there seems to be a concentration of electrons in and around the left-hand side of that atom. And so if I'm comparing, again, doing the same thing I did with the polar molecules, I can see that because this side seems to have a little bit more, I'm going to put a partial negative, delta negative on this side, and a delta positive on this side, just like I had a woolly section over here and a non-woolly section over here. The fact that this is occurring, despite the fact that we have electron neutral molecule, gives us a momentary dipole. Now, why do we call it a momentary dipole? It's this way because through electron movement, there are times where a positive, a partial positive, and partial negative can occur. And the thing about both of those it is temporary because the electrons can move on their own back to the original neutral position. So based on this answer right here, based on this idea of a momentary dipole, what we can conclude is that momentary dipoles can help neutral atoms or nonpolar molecules attract each other through the random motion of the electrons in that atom or molecule. That's the ultimate conclusion that we can draw. Through this random motion, where again, we have to reiterate, this is a temporary kind of thing. The bob sheep were all evenly distributed 1 minute, then they went back, then they went to undistributed. Then they went back to being distributed, then undistributed, distributed, undistributed. This happened over and over and over again. As those sheep move around the field, they go from one state to another, and same with the electrons. We started with neutral, even on all sides. Now it's unbalanced, and a minute later it's back to being balanced, and a minute later it's back to unbalanced, and a minute later it's back to balanced. It goes back and forth, back and forth, back and forth. So even though atoms themselves are electrically neutral, this momentary imbalance creates what is called a momentary dipole or a temporary dipole. And those interactions are known as dispersion forces, sometimes referred to as van der Waals forces, to help those molecules attract each other. So what causes this dispersion force to occur? Random movement of electrons forming temporary dipoles. How are they similar? Temporary dipoles attract each other similarly to dipole forces. And so that is what makes them similar to each other. The attractions, however, are temporary, not permanent, resulting in weaker interactions. Now, these challenge questions are interesting, but we do not have to go through them, and I'm not going to in this video. I would direct your attention toward the answer key in Blackboard if you're really interested in those. We're not going to get too deep into the answers there. But if you're interested in kind of extending your knowledge and understanding, go ahead and give those a look. But that should be all for now. I'm going to close this out here. And we will talk more about how these types of forces interact with each other when we get into the discussion of physical properties in our next lecture.